Hello, and welcome to part 3 of the training course on the demographic evaluation of age and sex data. In part 3, we're going to develop some more of the ideas which we covered in parts 1 and 2 of this training program. Particularly, in part 3, we're going to cover 3 aspects. The first part, the subject of this current video, is to set out and explain the application of what is termed Beers's interpolation. In the second and third parts, we're going to take the information and the approach of Beers's interpolation and apply it to the evaluation of data on ages of mothers giving birth and evaluation of data on the age at death. So this video is going to be covering Beers's interpolation. What is the problem that needs to be addressed by means of Beers's interpolation? In many situations, we may have data available only in 5-year age groups or presented in 5-year calendar year periods, when ideally what we want is data by single years of age or for individual calendar years. Linear interpolation, in other words, simply drawing a straight line between the data points, might be considered to be a solution to the problem, but in many applications, the data which are being considered are far from linear, and so doing so would be contraindicated. Some 70 years ago, Henry Beers, an actuary, set out a more robust approach to this interpolation problem, and it is still known to this day by his name. It is called Beers's interpolation. So what we want to be able to do is to produce numbers at individual ages from quinquennial or grouped into 5 years data. And the way we're going to do this is to use Beers's modified 6-parameter interpolation formula. The rationale is that he presents coefficients which form a 6-parameter polynomial, which is designed to minimize the forth differences between the original data and the modified interpolated data, and which includes an element of smoothing. Despite the robustness of this approach, one may still need to manage the extremes of the range, subject to interpolation, to avoid undesirable fluctuations of values, such as creating negative people or probabilities, or an odd shape of the population pyramid at their youngest ages. We will avoid this problem by interpolating usually over an age range beyond that which we're normally interested in. How would we go about using Beers's modified formula? I'm going to briefly set out the logic of the approach before demonstrating its practical implementation. Beers's modified formula is used to derive a smoothed single-year age distribution from data presented in 5-year age groups. And it is designed and set up to exactly reproduce the numbers in each age group. So, for example, that the sum of the smoothed estimates for ages 5, 6, 7, 8, and 9 at individual single ages will sum to the original total of that 5 to 9-year-old population. The coefficients which Beers derived in order to implement his modified formula are unfortunately tabulated in a rather unintuitive way. The coefficients are split into 5 panels, each containing a 5x5 matrix of coefficients. The first panel, panel 1, will be used for the first age group you are working with. The second panel for the second age group you are working with. The very last panel, panel 5, will be applied for the last age group you are working with, and panel 4 for the second last age group, which is subject to consideration. And we'll use panel 3, the middle panel, for all the other age groups. So on the screen here, we have on the right-hand side the coefficients which Beers derived. I apologize if the numbers are small, but the values are presented in the spreadsheets which accompany this workshop session. One thing to note is that within each panel, for example, this first panel over here, the sum of all those coefficients will sum to 1, as will the sum of those coefficients sum to 1, as will the sum of the coefficients in the very last panel. Summing along each row will show that the sum of those coefficients in every row is equal to 0.2, or 1/5 of the total of 1. And finally, we can note that the entire matrix is symmetrical along the primary diagonal. So for example, this value of 0.3333 here in the very top left-hand corner is the same as the value of 0.3333 in the bottom right-hand corner of the matrix. And we'll be using these coefficients to apportion the data in 5-year ages into single years of age. So how to go about implementing Beer's modified formula? The steps are as follows. First, you need to identify the appropriate panel's coefficients you are working with. For example, if you're working in age groups 0 to 4, 5 to 9, 10 to 14, and 75 to 79, in other words, those are the data which you are presented with, you'd use panel 1 for the first age group, 0 to 4, panel 2 for the 5 to 9 age group, panel 3 for the 10 to 14 through to 65 to 69 age groups, the fourth panel of coefficient for the 70 to 74 age group, and the final panel for the 75 to 79 age group. I apologize for the typo on that slide at this point here. Then each row will refer to the ages in that group. So if you're looking at the 10 to 14 age group, which in the example above would require panel 3 being the third age group, row 1 of panel 3's coefficients would provide the estimates for the population single age 10. Row 2 of panel 3 will provide the estimates of your population at age 11, and row 5 of panel 3 would provide the estimates for age 14. Then what we'll do is we'll apply the coefficients in each row to the 5-year age groups. In Excel, we'll use the sum product function as follows. If for panels 1 and 2, we apply the coefficients for panels 1 and 2 to the first 5 age groups. For panels 4 and 5, we apply those coefficients to the aggregated data by age group for the last 5 age groups, remembering that there are 5 coefficients in each case, in each panel. And for panel 3, we'll apply to the age groups centered on the age group that you are looking at. So, as before, if we wanted to split the data given to us in age groups from 0 to 4 up to 75 to 79 into single ages, we'd apply the panel 1 coefficients to age group 0 to 4, 5 to 9, up to 20 to 24, and each row of the panel coefficients will give us the estimate for the population at age 0, 1, 2, 3, and 4. We'd apply the panel 2 coefficients to the same age groups, 0 to 4, 5 to 9, up to 20 to 24, to give us the estimates of the single age populations from 5 through 9. And as a final example, we'd apply the panel 3 coefficients to the age groups 20 to 24, up to 40 to 44, which in this case would be centered on those aged 30 to 34, to give the estimates of the single age population at ages 30, 31, 32, 33, and 34. This might all sound both confusing and confused. It is much clearer with an example. So the data alongside are retrieved from the 2012 census conducted in Zimbabwe, presented in the conventional 5-year age groups. We can see, for example, that there were just under 2 million enumerated Zimbabweans aged 0 to 4 in 2012, and there were about 88,320 Zimbabweans enumerated at age 75 to 79. And we might want to, and there might be need to, and it's certainly, as we'll see in parts 2 and parts 3 of this material, why we might want to be able to derive a distribution based on these data by single years of age. So we'd want to know, of these 1.982 million Zimbabweans aged 0 to 4 in 2012, what is our estimate of those aged 0, 1, 2, 3, and 4? If we do not have the underlying single year age data. So this is a plot of those Zimbabwean data by 5-year age groups. We see the age groups running along the x-axis here, and we see the count going up the vertical axis. And we can see that this represents a typical relatively high fertility population, with very few people at the oldest ages and a large proportion of the population at very young ages. There's some kinks in the data. We see, for example, that the numbers aged 5 to 9 and those 10 to 14 are roughly the same. And one would wonder, looking at these data, as we did in part 2 of this training workshop, whether or not there might be some error in the enumeration of children aged 5 to 9 or 10 to 14 in these data, which has given rise to that. Alternatively, the explanation might reside in the changing patterns of fertility or mortality in the country around the time that the census was conducted. How would we actually go about deriving these single-year estimates? And this is a grab from the spreadsheet which accompanies the session, which I'll be demonstrating just now, of showing how we can use the coefficients produced by Beers to derive those single estimates of the population. What we have in the major body here are the coefficients from the Beers approach. I drew attention to that value of 0.333, for example, in the upper left-hand corner of the matrix. And so these 5 columns over here really just represent the coefficients tabulated by Beers and captured in a spreadsheet. And what we do to apply Beers's formula is we apply these coefficients to the appropriate age groups of the data. Going along the top here, we have a subset of the data which we had, the 1.982 million enumerated Zimbabweans aged 0 to 4, for example, and we have the numbers by age group transposed along the top there. And what we will do in each case is that we will apply the coefficients for each panel. This is the first panel here in the light blue. The 5 to 9 is the second panel, which is marked in the darker blue. And then from 10 onwards up to around about age 64, we have the orange panels, these yellow shaded panels, which are the third panel of coefficients. And you can see, in fact, that they get duplicated, that the coefficients for group 1 at age 10 is the coefficient for group 1 at age 15, and so on. So in each case, for each 5-year age group, for the middle panel, we reproduce those coefficients as required. Now, if we were wanting to derive, using Beers's formula, the number of people at exact age 4, what we would want to do then is we would take these coefficients, which are tabulated and provided to us by Beers, and we would apply them to the data in the first 5 age groups. And we'd do this by cross-multiplying. So we'd take the 0.0819 multiplied by 1.982 million plus 0.1508 times 1.695 million, etc., and adding the final element of 0.0115 times the 5th element of this column, which is the number for the 20 to 24 age group, 1.197 million. And we would sum all those cross multiplications together using the sum product function in Excel. When we do that, it produces an estimate of the number of people at exact age 4, 364,605. And if we were to do this for all of the first panel, as we've done over here, and sum the estimates to age 0s 1, 2, 3, and 4, the fitted numbers, as you can see along the second row at the top here, exactly correspond to the actual numbers originally provided to us. Likewise, if we wanted to get an estimate of the population at exact age 16, which is in the 15 to 19 age group, we would take the coefficients appropriate to age 16, which are these coefficients marked along here, and we'd apply those coefficients to the population such that it is then centered on the 15 to 19 age group, Remember, for the third panel, these yellow shaded coefficients, we apply those coefficients to the age group centered on the age group which we're looking at. Here, this is the 15 to 19 age group. And so we would take the coefficients tabulated and apply them to the sequence of 5 coefficients, 5 to 9, 10 to 14, 15 to 19, 20 to 24, and 25 to 29, centered on the age group which we are busy working with, which is the 15 to 19 age group. And so here we take that coefficient of 0.0020 and multiply it by the observed population age 5 to 9. Add to that the coefficient for group 2, 0.0160, multiplied by the population age 10 to 14. Add the coefficient for group 3, 0.22, multiplied by the population age 15 to 19, etc. for the last 2 age groups, and would sum all those results together to give us an estimate of the population aged exactly 16, or 294,051. And what you can see us producing going down this column is then a sequence of fitted values by single years of age, which exactly reproduce the aggregate in each age group, but provide us with a smoothed series of data by single years of age. In the case of the Zimbabwe 2012 data, however, we did actually have the original actual data. And this is shown in this plot here. This is a plot by single ages from the Zimbabwean 2012 census by single years of age going up to 79, and the counts enumerated by single years of age. The orange line shows the single year age distribution as enumerated in the data, and one can see certain heaping at age 50, 60, 65, and 70, for example, as well as a rather odd spike at age 12, which would be a consequence of births reported to have occurred in the calendar year 2000. So there's some rounding of births in that year. And that would also explain the rather odd 5-year age distribution, which I showed on a previous slide. The fitted data from the Beers interpolation formula is shown in the blue line on this plot, and I think you will agree that by and large it conforms incredibly closely to the actual data, although you can see here that the spike, for example, at age 10 does result in an increase in the fitted single years of age distribution. In other words, it doesn't completely eliminate what might be a substantive error in the data, but certainly attenuates it, and the effects of heaping at other ages are almost entirely neutralized. So how would one actually go about implementing Beers interpolation? A copy of the spreadsheet, which I'm going to demonstrate shortly, is on the training course shared drive, and it's called beers_zw.xlsx, the ZW standing for Zimbabwe. Once you have understood the logic of the spreadsheet, you might want to modify it to suit any other purpose. For example, in terms of a different range of ages, if you wanted to smooth your own country's data. But the same approach can also be used, as we'll be doing in parts 3, part 2, and 3, to derive single calendar year estimates from 5-year calendar results. This is going to be particularly useful in the context of the UNWPP data, that is data from the UN World Population Prospects, for which many important results are only published for 5 calendar year periods. And to help you in implementing this, I have prepared a bespoke spreadsheet to do this, and that will be demonstrated in the next two sections of this part of the training course. But now I want to show you the spreadsheet, this beers_zw.xlsx spreadsheet, to show you how it actually gets implemented in Excel. So this is the spreadsheet which we use, and this contains the original data as presented. Data by 5-year age groups from 0 to 4, up to 75 to 79, tabulated from the 2012 census conducted in Zimbabwe. And those are our raw input data. Off to the left here, we have the tabulated values of the Beers coefficients, We have the data for the first panel, the second panel, the third panel, the next to last or the fourth panel of data, and the last panel, the fifth panel of coefficients. And the color shading demonstrated here in the original tabulation is meant to draw your attention to which panel of data the various coefficients apply. Remember, I said that the first panel applies to the first age group, the second panel to the second age group, the middle panel to all but the first two and the last two age groups, going from age 10 to age 69. The fourth panel will be used to apply to the 70 to 74 age group data, and the final panel is the data of the coefficients to be applied to the final age group, the 75 to 79 age group. I also present here that original tabulation from Beers's coefficients, which was sourced and reproduced in Siegel and Swanson's 2004 volume, Methods and Materials of Demography, on page 728. So now we're going to look at how to implement and apply these coefficients sequentially to the data. What we have now shown on the screen, and now that I've expanded it, are the same data originally here presented, but now transposed, so those data now run across the columns rather than down the rows. And so we have the data for the 0 to 4, 5 to 9, 10 to 14 age groups as originally presented and as originally used. In order to derive the fitted estimates at each single individual years of age, we take those coefficients, the Beers coefficients, and we apply them using the sum product function. The arguments of the sum product function is to basically say, take elements of one scalar and cross multiply them by the elements of another scalar and multiply the results together. So for age 0, for example, this says take the sum product of the information the scalar contained in cells M7 through to Q7 and cross multiply and add them with the numbers in the population at the first 5 age groups, 0 to 4 up to 15 to 29, and doing each of those cross multiplications to then produce the sum of which then results. At age 7, for example, we would take the coefficients appropriate for the third row of the second panel, which is for the 5 to 9 age group, and we'll take those coefficients and apply them to the first 5 age groups again, as Beers's formula requires. For the exact age 18, we would take the coefficients for the fourth line, so that's 15, 16, 17, 18, so is the fourth row of panel 3 from Beers's coefficients, and we would apply those coefficients sequentially to the range of ages centered on the age group we're looking at, in this case, the 15 to 19 age group. And likewise, if we wanted for age 41, we would be taking the coefficients for the second row of a middle panel, and we'd be cross-multiplying those by the numbers of the population in 5-year age groups, centered again on the age group for which we're currently looking at, 41 clearly falling into the 40 to 44 age group. And when we do this throughout, we can then produce the tabulation of the fitted results by single years of age, and we can plot those. Sorry, I need to get, I don't know why it's not working. We can plot those results to produce the results which we originally wanted to produce. A reminder that if you have any queries or questions on this material, please email me, thomas.moultrie@un.org, copied to the ESCAP CRVS team, escap-crvs@un.org. I will do my best to answer the questions, either by return of email or in the first plenary session to be held on the 27th of May, 2022. I look forward to seeing you and joining you there during that session. Thank you very much.